Namaskar students. In this video, we will discuss some problems on improper integral. If you have seen the previous video, in the previous video we have discussed that what are improper integrals. Then we have two kinds of improper integral, first kind, second kind. We have discussed that if the limits of integration are not finite, they are in the form of minus infinity or infinity, then the improper integral is of first kind. And if the function is unbounded in the closed interval AB, which is the domain of integration, in that case, we call improper integral as improper integral of second kind. So we have discussed all these things in our previous video. We have discussed that how we will be solving such improper integrals, how we will be checking whether these improper integrals exist or not, they are convergent or not. So based on that discussion, here we'll be taking some problems on improper integral. So the first problem is here, we have to evaluate this improper integral provided that it exists. If it exists, we will be finding that what will be the value of this improper integral. So when we are solving or checking any improper integral, the first thing is here to check what is its kind, whether it is of first kind or second kind. So if you will see here this integral, since the limits are minus infinity and infinity, so it is very easy here. We can check here that it is of first kind because the limits are not finite. So if it is of first kind and here both the limits are infinite, minus infinity and infinity. So what we'll be doing here, we will be splitting this integral into two integrals with the help of some real number, because we have discussed all these things in our previous video also. So we will be splitting this given integral into two integrals with the help of some real number, say a. So this will be the first integral. It is an improper integral because its lower limit is minus infinity. And the second integral will be having its lower limit as a and upper limit will be infinity. This is again an improper integral of first kind. Now, after splitting it into two integrals, here both of these two integrals are improper integrals of first kind. We will be checking for both of these integrals. If these integrals exist, then the integral which is given here in the problem, which is present on the left hand side, that will also exist. Now let me give an idea that how we will be checking for both of these improper integrals which are present on the right hand side. If I talk about this first one, now here this upper limit is fine, a is fine, but here this lower limit is infinity, minus infinity. So for this first improper integral, we will be considering an integral of this type, c to a. This a will be same, but instead of minus infinity, we will be considering c, and after evaluating this integral, we will be considering here limit c tending to infinity. This is for this first one. Now, if I talk about the second one, for the second one, this lower limit should be kept same a because this a is finite, and this upper limit we will be changing, let it be b. So here for the second integral, now the limits which we will be considering will be a to b. The integrand is same, and after evaluating this integral, what we will be doing, we will be considering here the limit of this b, because here we have infinity. So we will be considering here that this b which we have assumed here as upper limit, that this b is tending to infinity. Here let's make one correction, it will be from minus infinity. C will be tending to minus infinity because here what is the limit? Limit is minus infinity. So here in this first case, this c will be tending to minus infinity, and for the second improper integral, this b will be tending to infinity. So as we have discussed, let us evaluate these integrals, and after that let us find out these limits. So let us start with this first improper integral, which is present on the right hand side. So consider this integral c to a x e raised to the power minus x square dx. We will be solving this integral with the help of substitution. Let x square is t, and after this substitution we will get here that x dx will become dt by 2. After this substitution we will get that this integral, which we are evaluating within the limits c to a, this will become c square a square and e raised to power minus t dt by 2. Let us integrate it. Minus 1 by 2 e raised to power minus t, and the limits are from c square to a square. Let us put here these limits. Minus 1 by 2 e raised to power minus a square minus e raised to power minus c square. We can, let us name this first as equation 1. Let us name this as equation 2. So what we get here, we have obtained the value of this integral. We have obtained the value of this particular integral. This integral we have obtained. Now after finding this integral, we will be taking here limit c tending to minus infinity. Now limit c is tending to minus infinity. The integral is this c to a x e raised to the power minus x square dx. Limit c is tending to minus infinity. Let us put the value of this integral which we have evaluated, which we have in the second equation. Minus 1 by 2 e raised to power minus a square minus e raised to power minus c square. We have c here, e raised to power minus c square, e raised to power minus infinity. So it will become 0. This second term will become 0 on taking the limit. So what we will get? We will get minus 1 by 2 e raised to power minus a square. So this is finite. So this first integral, which is present in this equation 1 on the right hand side, we have evaluated that this first integral is convergent and it will be equal to this limit, means it will be equal to minus 1 by 2 e raised to power minus a square. So we can write here, this means this integral minus infinity to a x e raised to power minus x square dx is convergent. And what we have? We have that this integral will be given by the limit which we have evaluated just now. Limit c tending to minus infinity. The integral which we had considered, we're having limits from c to a, x e raised to power minus x square dx. And what is this limit? This is minus 1 by 2 e raised to power minus a square. So we have solved the first integral. In the similar way, we can solve this second integral. Let us name this as equation 3. Now for second one, again we will be using the same type of substitution, and I am writing here directly now that similarly what is the second integral? We can see in this equation 1, this integral a to infinity. Before writing that integral, let us write down that what will be the expression for this integral, which is within the limits a to b. Similarly, this integral a to b x e raised to power minus x square dx. How we can write it? We can write it from this second equation. When we were having from c to a, then we were having this one, and now we have from a to b. A to b, so it will be minus 1 by 2 e raised to power, upper limit is here b, e raised to power minus b square minus e raised to power minus a square. Now let us consider this limit which we have discussed here, b tending to infinity. Let us consider this limit. Limit b tending to infinity. Why we are considering this limit? We have already discussed it. This one, limit b tending to infinity. Let us put the value of this integral, which is minus 1 by 2 e raised to power minus b square minus e raised to power minus a square. And when we will be considering this limit, we will get here 1 by 2 e raised to power minus a square. Because if I talk about this term, when we will be putting here b as infinity, e raised to power minus infinity will tend to 0, and we will be left with only this second term. And here we have minus, here we have minus, so it will reduce to 1 upon 2 e raised to power minus a square. Now again, we are getting the limit here. Limit exists, it is finite. It means the second integral which we have on the right hand side, that also exists and is convergent. We get the integral, the second integral which is present at the right hand side is a to infinity x e raised to power minus x square dx. We can check here, it is from a to infinity, and this is limit b tending to infinity. We have considered this integral. and here we have shown that it is equal to 1 upon 2 e raised to power minus a square, and let us name this as equation 4. Now, from equations 3 and 4, we have this integral which we have to find out. This integral, we have written it as sum of two integrals minus infinity to a with the help of real number a. Now we have evaluated both of these integrals. The results are in equation 3 and 4. If we use equation 3 and 4, the first integral is minus 1 by 2 e raised to power minus a square, and the second integral is 1 upon 2 e raised to power minus a square, and they will give us 0. And 0 is finite. So this integral exists and it is equal to 0. So in this way, we will be solving the problems of improper integral. First of all, identify that what is its kind, and then check what is the case whether lower limit is in infinity, upper limit is infinity, whether both limits they are infinite in nature. And if it is the case of second kind, then check if the function is unbounded, then the point where the function is unbounded, that point is the end point, or it is lying within the interval. So identify all these things and then proceed further for evaluating these improper integrals. Let us consider one more problem. The problem is we have to evaluate this integral if exist. Again, it's the same thing. If this integral is convergent, then find out the value of this particular integral. Now let us check whether it is improper integral or not. And if it is improper integral, then what is its kind? It is of first kind or second kind. See here, the limits are 0 and 2. They are finite. So it is not the improper integral of first kind. Now let us check for the second one. The integrand is here 1 upon under root 4 minus x square. Is it bounded within the domain of integration, which is the closed interval 0 to 2, or it becomes unbounded at some of the point of this closed interval 0 2? Yes, if we will check this, and if we consider x as 2, which is one of the endpoint, if we consider here x as 2, this new denominator will become 0, and hence this 1 upon under root 4 minus x square will become infinity. So this function, this integrand is unbounded at x equal to 2. At x equal to 2, the integrand is unbounded. So it is an improper integral, and this improper integral is of second kind. So the domain of integration is here. If I take this as 0 and this is 2, this is our domain of integration, and this is the point where the function becomes unbounded. So for checking the convergence of this improper integral of second kind, The integral which we will be evaluating will be, since we don't have problem with this lower limit 0, the function is bounded at 0, it will be same 0. And here be careful whether it will be 2 minus epsilon or 2 plus epsilon. Since if we take here 2 plus epsilon, we will be out of this domain of integration. So it will be considered as 2 minus epsilon. So we will be evaluating this integral, and after evaluating this integral, we will be considering here the limit that this epsilon is tending to 0. And if this limit exists, is finite, then this integral will exist. So let us consider this particular integral first, which we have discussed here. We have discussed all these things here. So consider, first of all, mention here that this is an improper integral of second kind. The function, the integrand, 1 upon under root 4 minus x squared. This is unbounded at x equal to 2. Now let us consider this integral 0 to 2 minus epsilon. These are the limits. Dx, it is here 4 minus x square. Dx divided by under root 4 minus x square. It's a very easy integral, direct formula we will be using here. So if I use that formula, it will become sine inverse x by a is here 2, and the limits are from 0 to 2 minus epsilon. Let us consider these limits. Sine inverse 2 minus epsilon upon 2 minus the sine inverse 0, and we will get here sine inverse 2 minus epsilon by 2. Now, after evaluating this integral, let us find out this limit. Now, limit epsilon tending to 0 in this integral which we have evaluated, 0 to 2 minus epsilon dx upon under root 4 minus x square. It will be limit epsilon tending to 0, and let us put this integral. This is sine inverse 2 minus epsilon upon 2. It will be sine inverse 1. If we put here epsilon as 0, we will get sine inverse 1, and sine inverse 1 is pi by 2. It means this limit exists and it is pi by 2. Since limit is finite, it exists. So the integral which we are finding here, this improper integral, it also exists. It is convergent and it will be equal to pi by 2. We get that the integral which we have to find out, this improper integral exists. It will be given by this limit and this limit is, we have evaluated here that this limit is pi by 2. So this will be the answer here, that this is pi by 2. Here write one line that the given improper integral is convergent. because the limit exists and is finite. And after that, we are evaluating, we are writing here that this integral is equal to pi by 2. Let us consider one more problem. The problem is, we have to here, the question is, prove that, it's an important problem, we have to prove that, important result also, prove that the integral, the limits are from a to infinity, dx upon x raised to power p, where we are saying that a is greater than 0, we are saying that p is greater than 0, is convergent, is convergent if p is greater than 1 and divergent if p is less than equal to 1. Let us prove this result. First of all, let us check that what is the type of this improper integral. Since the upper limit is infinity, so it is an improper integral of first kind. So here we will be considering two cases, because here the integrand is 1 upon x raised to power p. So depending on the value of p, we will be writing this integral. So we'll be considering here two cases. The first case will be when p is not equal to 1. This will be first case. And the second case which we will be considering will be when p is equal to 1. So let us consider these cases. Consider p not equal to 1. Now let us discuss here that since the upper limit is infinity, so the integral which we will be considering, that will be of form this. The limits will be from a to c. We need to change which limit? Upper limit, because the upper limit is infinity. We will be considering limits a to c. 1 upon x raised to power p is our integrand dx. And after evaluating this integral, we will be considering here that this upper limit, which is c, it is tending to, because here what we have, infinity, it is tending to infinity. So this will be our approach. So consider the first case when p is not equal to 1. Now let us consider this integral 1 upon x raised to power p dx. It's very easy to integrate. It will become x raised to power minus p plus 1 divided by minus p plus 1 within the limits a to c. This will give us, let us consider the lower and upper limits to evaluate this definite integral. We get here 1 minus p and c raised to power minus p plus 1 minus a raised to power minus p plus 1. Now here what we have to consider, that the c is tending to infinity. So we have evaluated this integral. Now let us consider the limit, that this upper limit c is tending to infinity. Limit, upper limit c is tending to infinity, 0 to c, dx upon x raised to power p. This become limit c tending to infinity 1 upon 1 minus p, and what we have here, c raised to power 1 minus p minus, here we have a. So let us correct it. It is a. Here it is a. In the problem it is a. So make here this correction. It is a. This is our upper limit. C, this one, minus a raised to power 1 minus p. Now let us find out this limit. Now this, here we have c raised to power 1 minus p, and what we have considered that p is not equal to 1, means this 1 minus p will not be 0. Now if this 1 minus p is positive, and here c is tending to infinity, if this exponent 1 minus p is positive, this exponent of c 1 minus p is positive, in that case, if we are taking the limit, that limit will be infinity because the exponent is positive. But if 1 minus p is negative, this c raised to power 1 minus p, this 1 minus p is negative, means then this, if the c is tending to infinity, it means since exponent is negative, this will, infinity will go in denominator and 1 upon infinity will become 0. So in that case, the limit of this c raised to power 1 minus p will become 0 if 1 minus p is negative. So again here we need to consider two cases depending on that what is the sign of this exponent 1 minus p. 1 minus p is positive, 1 minus p is negative. So let us consider two cases. Let it be case A. If 1 minus p is positive, means 1 minus p is greater than 0, that is p is less than 1. Now 1 minus p is positive, c is tending to infinity, this term will tend to infinity because the exponent is positive. This infinity will come in numerator, so this term will not exist, it will tend to infinity, and hence this complete limit will not exist because this term is tending to infinity. So in this case, this limit c tending to infinity, c raised to power 1 minus p, this tends to infinity, and therefore this limit, this complete limit which we were evaluating here, this does not exist. And now since this limit does not exist, it means the improper integral for this particular case, that p is less than 1. For this particular case, this improper integral will not exist, will not converge, and it will be divergent. So here for p less than 1, integral, the given integral is not convergent. So this is the first case when this exponent 1 minus p is positive. Now consider the second case. Let us name this as case B. These are the sub cases within the case that p is not equal to 1. So if this exponent of this power of c is negative, means 1 minus p is less than 0. That is, p will be greater than 1, and in this case this limit c tending to infinity, c raised to power 1 minus p, this will exist and it will tends to 0, because here this exponent is negative. This 1 minus p is negative. So this limit will exist and it will be tending to 0. And therefore, this integral a to infinity dx upon x raised to power p, which is equal to this limit c tending to infinity, c raised to power 1 minus p minus a raised to power 1 minus p, this whole divided by 1 minus p, it will become a raised to power 1 minus p, and here we have minus sign, so let us write this as p minus 1. Since a is finite here, this will exist and is finite. So in this case, the integral, improper integral for p greater than 1 is convergent, and the value of the integral will be this a raised to power 1 minus p divided by p minus 1. So for p greater than 1, what we are getting, that the integral is convergent. Thus, for p greater than 1, the given integral is convergent. Let us see the result which we have to prove. We have to prove that for p greater than 1, it is convergent, and for p less than equal to 1, it is divergent. So we have covered the two cases, greater than 1 and less than 1. We have shown that for p less than 1, it is not convergent. Here, it will not convergent means divergent, and for p greater than 1, we have shown that it is convergent. Now let us consider the case 2, when p is equal to 1. In this case, the integral a to infinity dx upon x raised to power p, this becomes a to infinity dx upon x. What we have done, we have put here this p as 1. And consider now this integral a to c dx upon x, it will be log x, and the limits are from a to c. We will get log c minus log a. So after evaluating this integral, let us find out the limit. When this c, this upper limit, is tending to infinity, c is tending to infinity, this a to c, this will be limit c tending to infinity. Let us put the result for this integral, which is log c minus log a. Now here we have log c and c is tending to infinity. So it will not exist, it will not be defined, because limit c tending to infinity, log c will be infinity. Here, limit c tending to infinity, log c is tending to infinity. Therefore, this limit c tending to infinity, log c minus log a, does not exist. So for this particular case, for p equal to 1, the given integral, the given improper integral is not convergent. So in this way, we can do the problems of improper integral. So thank you for now. Thank you. Have a nice day.